Hello, here we are again. This is the video lecture number 2 of Physics 2A. So Physics 2A, video lecture 2. And I'm just going to start off with some announcements while I have your attention. So until further notice, we're just sending the Monday, Wednesday, and Friday lectures to krundy@csufresno.edu, where the subject is your name and then Physics 2A homework. Now, the lecture notes will always be sent on Friday by 6 o'clock, and it will be the Monday, Wednesday, Friday lecture notes. So this week there's only 2 lectures, of course, the first week of the semester, so you just send me the Wednesday and Friday lecture notes. That is to say, video lectures 1 and 2. Send those notes to me. Now, the homework that I assign out of the book, say, and elsewhere, the homework problems, you will send the Friday, Monday, and Wednesday homework problems. So I will assign some problems at the end of this lecture, but they are due in next week's email, okay? Because you need possibly more than the rest of the day. So you can, of course, take your notes and send them to me, but the homework problems that I assign today will be sent next week. So that's what this means. You send Monday, Wednesday, Friday lecture notes in this email, and you send the Friday from the previous week, and then the Monday and Wednesday lecture notes. So for this week, of course, I'm sorry, Friday, Monday, Wednesday homework problem. So for this week, you will just send that problem that I gave last time concerning that little geometry problem. That will be the only problem you send in. And in fact, I'm going to solve it today, so you get that for free. But that's the way it is. Good. So, and if any of this confuses you, just keep it simple, nothing to worry about. You're sending in your notes and your work. Okay, so let's get started. Put that up here. So the problem that I'm going to solve, and we'll get around to our little geometry problem, is the question of the shape and size of Earth. So how big is our Earth, and before that, what shape is it? Now, this is a topic that I think every educated person should be aware of, and it's not in our book, but I like to put it at the beginning of the semester because it leads us right into some interesting stuff and important stuff. So what we'll call our topic here, shape and size of Earth. Of course, normally with a bunch of students in front of me, we can have a back and forth and kind of tease out the answers to this. But here I'm just going to have to deliver it to you. So first of all, the shape of Earth. How do we know our Earth is a sphere? We've seen pictures of our spherical Earth. Nowadays we just know it, but how do we know that in the absence of that kind of information? Put yourself back a few thousand years in time. So the shape that it's spherical was inferred by the ancients in a couple of different ways. One way is they pointed to the sun and the moon and they said, well, if the Earth is a heavenly body, those are both spheres, the Earth would also be a sphere. They actually saw that the Earth cast a shadow on the moon during a lunar eclipse, and that shadow had an arc shape. I'm going to draw a little picture that goes with that in a moment. And another thing one can do is actually be up on a mountain at the coastline and hold up a straight edge, and then you'll actually see a little bit of curvature. If you're looking over the ocean and on a high enough mountain, you'll see a little bit of curvature under that straight line. Okay. So those are all ways to discover that, but just for putting something up here, let's say Earth casts an arc-shaped shadow on the moon during a lunar eclipse. Okay. And there's a nice little picture that goes with that. Lunar eclipse. Yeah, you might want to look up something about a lunar eclipse. Yeah, the picture I'm going to draw is like this. We have our Earth. I'm going to say the sun is out here shining on the Earth. Then what's day and what's night? Well, if the sun is over here, this is our Earth, this is day and this is night. Okay. Now, if you ever see a lunar eclipse, say you're standing here on the edge of day and night, and out here is the moon. This side's in the shade, and you're looking at the moon. It's evening, and you're seeing a full moon. You're seeing a full moon rising. Okay. Now, if that moon is here, how about I use a different color? If that moon happens to be here, it casts a shadow on the Earth. Okay. If that moon is over here, then the Earth casts a shadow on the moon. And that shadow has an arc shaped in it, has a curvature to it, an arc shape. And the ancients said, well, only a sphere will always cast an arc-shaped shadow. So that's an interesting topic. You can look that up. Okay. That's how we know that the Earth is a sphere. So spherical. Check. That's supposed to be an E. Okay. So there's the shape of Earth. It's discovered to be spherical, and now the second question is the size of the Earth. How big is the Earth? Question mark. How big is the Earth? For example, this is a meter stick. This is 1 meter. How big is the Earth in meters? Now that it's a sphere, if you could just put a meter stick on the Earth and just go around the entire Earth, you got time. And how many meters would that add up to, for instance? Or if it's a sphere, then maybe if you know the radius, then you know the size of the Earth. So that's what we're looking for, the size of the Earth. And here's where our construction comes in. So, let's see, let's go ahead and draw a large sphere here. And I will put a famous name, Eratosthenes. This is a couple hundred years BC, a long time ago. Eratosthenes, he's working in Alexandria, which is on the Nile, Mediterranean. And he reads in a book that there is a well in a city down south where the sun shines directly down to the bottom of the well. Okay. The sun shining directly down to the bottom of the well means the sun is directly overhead at noon on some day of the year. Okay. This never happens in Fresno. Okay, get a globe out and you can start to understand that. So Eratosthenes knows that the Earth is a sphere, and he imagines here's the sun ray, light ray, and here's the Earth of radius r, and the sun's directly overhead, it shines down the bottom of the well. Now on the same day, Eratosthenes is up north here in Alexandria. Now notice, the up and down direction is always just away from the center of the earth. Okay. If you're standing down here, up would be the way my pen is pointing. Here it would be up, always away from the center of the earth. And so what Eratosthenes did was he said, well, on June 20th, that well is illuminated by an overhead sun. I'm here up at Alexandria, and the sun ray is coming in. I'm just going to draw it freehand. The sunlight is coming in like so. So I'm measuring an angle theta between the direct up and down and where the sun is coming from. You guys go outside at noon, and you'll see straight up and down versus the direction to where the sun is. That makes an angle. Okay? I just showed you how an angle is made. That is this angle right here. Okay. And you're seeing the construction we had there the other day. Radius, there's the arc length S, there's the angle theta that was measured, and the assumption was that the rays of the sun are close to parallel. They aren't exactly parallel, but he said, he used for his construction, okay, we're going to assume they're parallel. So I'm just going to write parallel. So yeah, that was S was equal to 800 kilometers in whatever units they used back then. Theta was equal to 7.2 degrees, I believe, or maybe 7.15 degrees. You can try out either. But yeah, this was the measurement that was made. This was the known north-south distance, north to south distance. And it was the distance between Alexandria and down here is Aswan. Aswan is where the Egyptians have a big dam on the Nile River. Okay. You can even look these up in the map. There's our problem, and Eratosthenes was able to discover the size of the earth because this is now a simple mathematical problem, and I'm going to solve it for you. I had given it, and because it's really typical of the type of thing we have to do in physics. We have to draw a sketch, right? We took a physical scenario now, we turned it into a sketch, and now we have to find an unknown or a relation. Okay. I'll send this up, and we'll use this board right here. So yeah, this is a world historic example. So here's the logic that he used. He said that this angle is to 360 degrees, right? It is a proportion of the entire 360 degrees of the circle. That is equal to the same ratio of that arc length divided by the circumference. Okay. So once you have that idea, essentially you're done. You just have to do another step of algebra. Okay. So again, in a small picture, or actually in the picture I have up here, we've got that angle. Oh, and now I see that I'm missing one thing here. The reason he could make that claim is because these two lines being parallel, this angle inside is equal to the one that was measured outside here. Okay. Now, so this fraction of the entire angle is equal to this fraction of the circumference, and solve for r. And of course, that's typical algebraic exercise that you want to do a lot of, and we'll do just infinite amounts of that this semester. So you can do a couple of ways. You could just invert both sides, so you'd have 360 divided by theta is equal to 2 pi radius divided by s, and then isolate the radius finally as s 2 pi, I was multiplying 360 divided by theta. And then, and only then, do you plug in numbers. Because right now, this would be true for any number of examples and not just Alexandria and Aswan. When you finally plug in the numbers, you're going to have, well, I'm going to leave that for you to do, okay? So you guys go ahead and plug that in and find out what you get. The established value, the one that is in our book, radius of Earth equals 6.37 times 10 to the 6 meters. Go ahead and see what you get here. It'll be close. Depends on how accurate these angles are measured after all. So those are the numbers I'm using. This is the number you'll find in your book. Speaking of which, the book has probably in the chapter on gravity a lot of astronomical data. And that would be in chapter 7. And various in the story. Okay, our book says 6.38 times 10 to the 6 meters. Radius of Earth at the equator. Should I change that? 3.7 is the one I always use, but this is the one you'll actually find in your book. This whole argument you will not find in your book. That's why I'm showing it to you now. Good, so you get that, and you've discovered the size of the Earth. Now, what have I done here? I've expressed this number in scientific notation. So if you plug in 800 kilometers, you're actually going to have to convert your answer from kilometers to meters, which is something we have to know how to do. And so this example here, besides this important piece of knowledge and wisdom, has a lot of interesting and important techniques that we'll be using in this class. So that's what I'm going to do next, is put up kind of analysis of what we just did here and talk about the techniques that we need, the mathematical techniques in physics. Good, so there we have the radius of the Earth. And like I said, this was assigned on Wednesday, so this you can bring in. It's part of the lecture notes anyway. Okay, you can send in to me on your email notes. Okay, good. Wonderful math problem. So let's see all that we had here, because this is part of the scientific method. So the ingredients here, we used observation, underneath and around the whole thing is, of course, creativity. Okay, but there were observations made, position of the sun, position of the moon, etc. So observations, and then we had a measurement. In this case, one had to know the distance between those two cities. One had to go outside and actually measure that angle with the angle to the incoming sun. So measurement, here we had lengths, angles. we had to have some geometry. My little sketch, of course, was geometry. And we had to do a little algebra. And you'll notice, again, I did everything without actually plugging in numbers. That's very important that we obtain a formula. And that we keep the formula general by not plugging any numbers in. The 360 could have actually been gotten rid of if we had the unit of radians, but we're starting out with degrees. So we'll leave the 360 in there. So we had geometry and algebra. We also had some arithmetic and scientific notation. And finally, we actually had a physical unit. We had a unit of length. Right? The answer only means something if we say those are meters. If it were inches, feet, miles, it would be a different number. So we had a particular unit of length. And in this semester, we're going to find that there are 3 basic units of physics that we can reduce everything to, and one of them is length. One of them is time, and one of them is, the third one is mass. Right now we just have the length, okay? The meter. So all of these things are the ingredients that we're going to be doing this semester, and I'll use the rest of the hour to talk about a little bit about scientific notation and also geometry and algebra. Just what the type of thing we'll be using in this course. I'll point out that your textbook has an appendix, if I'm not mistaken. Yeah, Appendix A. Yes, so Appendix A in the textbook has a mathematics review with a bunch of interesting stuff. So I'll put that as an assignment. This is not homework to turn in, but I'll just call it homework anyway. Read the Appendix A in the text. Have a look at it. You may say, well, I know all that stuff. If you don't, then you know you have something you could work on. Math review. And I'll do some math review right now for us. Let's see how much time we've got going on here so far. Okay, we're doing fine. So the next topic on our list is a math review. Yeah, one thing you'll notice, the book uses many numbers in the problems and stuff, and you won't see me plugging in many numbers. So there's a reason for that, and it's something you'll want to become accustomed to, just working with formulas, understanding them, being able to manipulate them. Good, so let's do a little bit of math review. I'm going to start out with the scientific notation problem. Scientific notation. But we'll just start with, let's say we wanted to do a division. 6, 8, 9, 1, 2, 3. I'm just going to make up some numbers divided by 0.44456. Hey, how about 0.04456? Now, what we want to do is we're going to learn not to be afraid of numbers. So we want to do this division without a calculator. Without a calculator, And we'll use scientific notation, and in fact, what we're going to do is approximate. Physicists learn to approximate, and so let's approximate the numerator. We could say 6.89 times 10 to the sum power here. 1, 2, 3, 4, 5. So times 10 to the 5. And then we could say we have 4.45 times 10 to the minus 1, 2. So minus 2. Okay. And that's already been approximated because I left off some of those digits. I'm going to approximate it even more. I'm just going to let this numerator be 7 times 10 to the 5. I'll do a crude approximation. I'll say we have 4.5 times 10 to the minus 2. Okay, what's 7 divided by 4.5? I don't know. I just put these numbers up here. But we got a rough estimate here. It's over 1.5. Okay, I'm just going to write approximately 1.5 times 10 to the, now let's go ahead and deal with these. We have 5, and this is a minus 2 in the denominator. Turns into a plus 2 up here, 1 plus 2. So I'm just going to call this 1.5 times 10, and it's still an approximation, times 10 to the 7. Okay. Now what I'll ask you guys to do is go ahead and use your calculator and then see how close we were. Because here we had something just confusing, and here we have something very simple and clear, okay? So that's the use of scientific notation and estimation. So let's go ahead and call it scientific notation and estimation. So this is one way to lose your fear of numbers, okay? And many, many digits is just a lot of confusion. Here we have something good. And my guess is that this is within several percent of the true answer, okay? But you can go ahead and look and find out. Good, so we've dealt with scientific notation. You can find more about scientific notation in the appendix. And if you want to have some fun, as it were, just make up a couple problems like that, go through them, and then see how close you are to the actual calculator answer. And that'll build confidence. Okay, next. A little bit of geometry and algebra to remind you of the type of things we'll be doing and using in this course. So when it comes to geometry, we need to use triangles quite often. So the first thing, I could just have some triangle. And what do I know about triangle? It's big enough? Yeah. I'll draw a little larger so we can do some analysis here. So how do we work with triangles? We can label the angles. We've learned that the sum of those three angles equals 2 right angles, or equals 180 degrees. We could prove it also if we wanted to. I'm just going to write alpha plus beta plus gamma, 180 degrees, 2 times 2 right angles. Another thing we know is that the area equals 1/2 base times height. So if we have B here and a height. So we use those kind of formulas. Triangles. Right triangles are very important. Okay, so then we have 90-degree angle here, alpha, beta, 90 degrees in a right triangle, and then of course the famous Pythagorean theorem. Okay, so there's triangles, circles and spheres. So we've got the circle, we've got circumference equals 2 pi radius, we've got area equals pi radius squared. And I'll put spheres here as well. Formula for a sphere of radius R, surface area 4 pi radius squared. Good, so those are just some basic facts of geometry. Fun to prove if you have time, otherwise we'll just accept them. And then we can algebraically manipulate these kinds of formulas. So right under here I'll say algebra, and we'll just do something with any of these formulas here. So for example, we've got the area of a sphere, and from A 4 pi radius squared. Suppose we're solving for the radius. Radius, we'd have area over 4 pi, and then we take the square root, and we often write the square root as the 1/2 power. You're familiar with that. So yeah, algebraic manipulations. And in a problem, you don't want to plug in numbers until the very end. Okay? If this were a problem and you were given some quantities here, you'd first solve this. That would be your answer, and then you could plug in some numbers and the number of the area. Okay, so that's an example of the kind of algebra we do, and we do quite a bit of it. We have. Should I go straight to the quadratic formula? Let's see what I have here. Look in your appendix for more examples of this. Now I want to show straight lines and parabolas. Equation of a line. Equation of a line. So that takes you back to your algebra class, and you have y equals mx plus b. And then you say, okay, m is the slope and b is the intercept. Okay, you can graph this. X, y, b, and it has some slope there. Good. Now, in physics, this equation is very important, starting next week. But it's going to have a slightly different form. So suppose I write x equals x0 plus b0t. And I say graph x versus t. X versus t. This is also going to be the equation of a line. So if I said graph x versus t, I'm going to set up a graph, t and x versus t, but it has a physical meaning. So t is going to be time and often measured in seconds. X is going to be position measured in meters, and x0 is going to be an initial condition. But everything you learned about the straight line is present here as well. We're using different letters, and these letters have meaning, and they actually have dimensions. So this T represents seconds, this X represents meters, both X's. So first thing I'm going to do is, see, the intercept, just happen to place it first here, that's x0, and then draw a straight line the way we did before. So what is this v sub 0? It's the slope, but it now has units. It has units. So we know about meters, the meter stick, okay. We know about seconds, the clock is ticking, we have seconds. So what is this unit, this thing here? Well, in physics, equations have to have the same units on both sides. Okay. So this is meters, V0 times T must also be meters. Okay. So I'm going to write first here, V0 is the slope. And this really important lesson. V0T has units of length, which is meters. V0T has units of length. So here's what we do. Put a square bracket around here, and the square bracket means we're taking out, we're analyzing what the units are. And since T is seconds, V0 has units of meters per second, which we'll learn about next week is a velocity. So this is an example, first of all, of the use of basic algebra, but now these quantities all have units. In this case, this is a length, as is this, as is that. And because V0 times T is a length, I can solve for the V0. Basically, I divided both sides by T, and I got length over time, meters per second. That's called dimensional analysis. I'm going to check the time once more. And yeah, we're coming on the end of the hour. So here's what I'll do. Call this dimensional analysis. So when we talk about a dimension, we're talking about the units of a quantity. So the dimension is either length or time, and coming later on, mass. But the first point is that in a physics equation, or in a physical equation, both sides must have the same units. Okay. So I'll do a simple version of our equation up there. X equals V0 times T. That means we would be going through the origin, okay, just a simpler version. So the square bracket means that I'm asking what are the units in this equation. And then we see we have meters, and on this side we have meters per second times seconds. And you can see the seconds cancel out, so we have meters equals meters. Okay. So that's what we call dimensional analysis. And in fact, throughout the semester, I'm going to introduce new quantity after new quantity. And the first thing we always do is do the square bracket thing and make sure we understand what the units are. Okay. So this is the first example of that. So we had the dimensional analysis. Good, so this is a good place to stop. What I'll write down now is just a couple of homework problems out of the text. You know, this textbook, instead of calling them chapters, they call them topics, but I'll just going to keep calling them chapters. So if you read chapter 1, what you'll find is at the end of each chapter there's a summary, there are conceptual questions, and then there are problems. And I always take the problems that I assign out of the problems. So in this case, I'm going to do homework, and this is for next week, of course, homework. So chapter 1, problems. And there are a couple of good ones here that I want you guys to look at. There's a trigonometry review, and there's some trig type of problems. But a nice one is problem 47. It uses circumference and angles. So it uses some trigonometry and a little bit of geometry. Very nice, simple problem. And '46, obviously not in order here, is also a basic trig problem. Now, problem 1 and 2 are dimensional analysis problems. Let's do that. Problems 1 and 2 are dimensional analysis problems. And we'll leave it at that, okay? These 4 are a good start, basic start. Next week we'll jump in with both feet. So enjoy all of this physics, enjoy your weekend, and we'll see you next week.